Let's take the derivative of the cotangent of arc cosecant of x. And we'll draw a right triangle to help us sort out what this trigonometric expression is saying. First, though, let's quick reminder that arc cosecant is a function which turns a hypotenuse over opposite side into an angle, and we'll call that angle theta, and we'll make it this angle. And that cotangent is a function that's going to turn our angle, which is in this case theta, into a adjacent side over an opposite side. So something to keep in mind is that with this reference triangle, these lines are not functions on the Cartesian plane. The reference triangle that we made is using vectors. So that's a vector, and it goes in the I direction. This is another vector, goes in the j direction. And this is just some scalar distance. That is the distance between the hypotenuse is that scalar distance, which just goes between the origin and the addition of these two vectors, and its direction. If you wanted to label it a direction, you would use this theta to do so. But as it is, this hypotenuse has only a distance and no direction. And to keep that in mind as we take a look at this, because if we say, for a convenient way to say arc cosecant of x, well, if x is hypotenuse over opposite, let's make the hypotenuse side equal to x and the opposite side equal to 1, because that's nice and easy. However, because this is just a scalar distance, it's an absolute value. So that actually doesn't work out for us, because if we have x, so let me try and think of a way to describe this. X can go we can move a distance that's a positive distance in a negative x direction. We can move a positive distance in a positive x direction, but the idea of a negative distance is just nonsensical. It doesn't mean anything. The distance between 2 points can't be, and this is another way of looking at it, a less rigorous way, but maybe having a different perspective will help, is that the distance between these 2 points, whether the triangle were to go down this way and we're to connect these points, or if it was to go off in this direction, I guess we can't have any room in that direction. No matter what direction we go in, the hypotenuse, the distance between here and the origin, is always going to be a positive distance, even if it's moving in a negative direction. So with that in mind, we do not want any function that could possibly be negative in the hypotenuse, because we're necessarily going to lose information. If we find out what this value is, the cotangent of arc cosecant of x, if we find out what that is, using a triangle where the x is in the hypotenuse, all our values for when x is negative are going to be wrong. So it'll only be true for positive values. So here's an easy way to fix that, is let's say the hypotenuse is equal to 1. And the opposite side is equal to 1 over x. because then you multiply the reciprocal, and that's the same thing. That is the same thing as saying arc cosecant of x is arc cosecant of 1 over 1 over x. So we can rewrite that like this, and we're not left with that dilemma, because 1 is always positive. And then we can just solve for this final side here using the Pythagorean theorem. So opposite squared plus adjacent squared is equal to hypotenuse squared. And opposite we have is equal to 1 over x. So we have 1 over x squared, which is the same thing as saying 1 over x squared. Adjacent we're going to leave alone because we don't know that yet. Hypotenuse is equal to 1. So we have 1 squared, which is just going to be equal to 1. And then we can subtract 1 over x squared from both sides of the equation. So we get adjacent squared is equal to 1 minus 1 over x squared. Take the square root of both sides, and you get adjacent is equal to square root of 1 minus 1 over x squared. We're only taking the principal root, the positive root, and we're not doing adjacent equals plus or minus the square root of 1 minus 1 over x squared for the same reason as we couldn't have a function that could possibly be negative in the hypotenuse, because this is a distance. So we're only taking the positive root because it is a positive distance. Now we can move this x here, could be negative, like it's not going to be an issue here because this is x squared, and x squared will always be positive, but that x can be negative, and in the opposite side it will be negative, and that will affect the outcome. But that's fine because it's not the plus or minus direction, it's a plus or minus x. So that's the direction aspect, and it's not a negative distance. So we're going to take the positive principal root and not plus or minus because this is a distance. So we have the square root of 1 minus 1 over x squared. That is horrible. Let me rewrite that. 1 over x squared. Okay, and now we have our triangle all sorted out, and y equals cotangent. Remember we said arc cosecant of x is equal to theta. So we have cotangent of theta. And cotangent is, like we said, adjacent over opposite. So the cotangent of theta is going to equal adjacent is square root of 1 minus 1 over x squared, and opposite is going to be 1 over x, which we can multiply top by the reciprocal of the denominator, and we get x times the square root of 1 minus 1 over x squared. And now we can differentiate both sides with respect to x. So dy dx is going to equal dx of, and I'll just copy and paste this, all this. And we've got a function. We've got a function of x times this function over here, and we're going to get dy dx equals, using product rule, we're going to get d dx of x times the square root of 1 minus 1 over x squared plus x times the derivative of square root of 1 minus 1 over x squared. Okay, and we can start taking some derivatives. So we'll say dy dx is equal to, derivative of x is going to be equal to 1 times square root of 1 minus 1 over x squared. And we're going to add to that x. And the derivative of all this, well, we can rewrite this like this. And then it's kind of clear to see that we have a function of 1 minus 1 over x squared nested within the square root, or the 1/2 exponent function. So let's call the internal part u, and we can move towards chain ruling. So we get u equals 1 minus 1 over x squared, and then we have derivative with respect to x of u to the 1/2 power. And since we have a function in terms of u and we're differentiating with respect to x, we're going to want to rewrite this using the chain rule. So du dx times d du of u to the 1/2. So for our u, we can rewrite this right-hand side, 1 over x squared, as x to the negative 2. That'll help us take the derivative. So this one's pretty simple. We can say that du dx is going to be equal to, the derivative of the 1 is 0, minus, so we have minus, well, we'll call that minus 1 times, bring down the negative 2 times negative 2 times x to the negative 3. The negatives cancel out, and 1 times 2 is just 1, so we can get rid of the 1. And we have 2 times x to the negative 3, which is 2 over x to the third. So du dx equals 2 over x to the third. We can bring that here. 2 over x to the third. And multiply that by derivative of u to the 1/2 is going to be 1/2 times u to the negative 1/2. So let's rewrite that as 1 over 2 times u, 1 over 2 times the square root of u. Looks like this 2 is going to cancel with that one, so we can get rid of that. Rewrite that as 1, and we can undo our u substitution. So we have the square root of 1 minus 1 over x squared. Because we just undid this u substitution with the negative exponent, so it's 1 over x squared. And finally, we can multiply that x cubed into the denominator. So we can extend this out a little bit and say x cubed. And just to clarify, that is a 1 in the numerator. We can bring down the x here, multiply that. Right off the bat, that's going to cancel out with one of the x's in the denominator, so we'll just get rid of that and rewrite that as 2. Get rid of that. The plus sign is going to come down. And we can bring down this bit, which 1 times the square root of 1 minus 1 over x squared is just going to be 1 square root of 1 minus 1 over x squared. So it looks like we're pretty much done, but I'll just rewrite this so it's a little neater. So dy over dx equals square root of 1 minus 1 over x squared plus 1 over x squared times the square root of 1 minus 1 over x squared. Copy and paste. So we can actually add these, and we'll be able to do a little bit more reduction. So currently we have square root of 1 minus 1 over x squared over 1. We can multiply the top and bottom by x squared times, well, this term again actually. So what we will get is multiply the top and the bottom by this value. So that square root is going to go away, and we're going to get x squared out here. Now these have the same denominator, so we can actually bring this plus sign up, connect this, so we just added them, and now we only have the one denominator. You can center it a bit. And then x squared times 1 is x squared minus 1 over x squared is 1. So we have x squared minus 1. X squared minus 1 plus 1. The minus 1 and plus 1 cancel each other out, and we have x squared in the numerator, and there's an x squared factor in the denominator, so those cancel out, and we're left with 1 over the square root of 1 minus x squared, and I'll rewrite this, or clean it up before I circle it. Center this nicely. Such an elegant solution. And although this is true, this is easier to work with, so I figured it would be nice to come back and give this little addendum. We are done.